Assalamu alaikum everyone. Welcome to the course of ME212 Dynamics. Today's lecture is lecture 26 and this is the continuation of your chapter 16. Today we will discuss about rotation of the rigid body about fixed axis. So in the previous lecture we talk about the translation and the general motion of the rigid body. So in general motion we discuss briefly about the rotation about fixed axis, general planar motion and the translation motion. After that we discuss in detail about the translation motion of the rigid body, and we come to the conclusion that when the rigid body translate, so each and every particle on that rigid body move with the same velocity and same acceleration. So in the translation motion of the rigid body, the relative velocity and relative acceleration term become zero. So that was about the translation of the rigid body. So today we will study about the rotation of the rigid body about fixed axis, which is the second motion, the second type of the motion of the rigid body. So rotation about the fixed axis. So in the previous lecture we discussed this thing in detail, that when the rigid body rotate about an axis, so the each and every particle on that rigid body has to move in a curvilinear motion except those particles which are on the axis of rotation. So consider that this is the rigid body. So this rigid body rotate about an axis. Let us say that that axis is a prime. So this rigid body rotate about an axis with an angular velocity omega or an angular acceleration alpha. So this means that each and every particle on that rigid body has to move about this axis a prime in a curvilinear motion or in a circular motion. Circular motion is a type of curvilinear motion. Consider that this is the particle P, and the location of this particle P from the fixed point or fixed axis is measured with respect to angle theta, which shows the position of the particle P. And this position is basically the angular position of the particle. So what will be the position of this particle from the axis from the center of the circle? This position is shown by vector r. So vector r is showing you the position of the particle. So the displacement of this particle is represented by theta from the fixed axis. So when this particle after some time move to a new location, let us say that this is a new location of the particle p prime. So the angular displacement is represented by d theta. So in the contrary to the rectilinear motion, for the angular motion, the position is represented with basically the angular position, where in the rectilinear motion we simply talk about the position, which is the simply the rectilinear position. But here in the angular motion we will talk about angular position, and the position vector r is simply the position of the particle p from the fixed origin O. So in the rectilinear motion we talk about the velocity and acceleration. Similarly, in the angular motion we will again talk about the angular velocity and angular acceleration. The difference between the rectilinear motion and the angular motion is that in the rectilinear motion we simply talk about velocity and acceleration, while in the present case the velocity become angular velocity and the acceleration become angular acceleration. So the angular velocity is basically the rate of change of angular displacement. So the angular displacement in this motion is theta. So the rate of change of theta is simply the angular velocity. So a convention we follow is that the counterclockwise direction for the angular velocity is positive. Similarly, what is angular acceleration? Angular acceleration is the rate of change of angular velocity. So angular acceleration will be represented by alpha. So this will be the d omega by dt. So, or in other words, it will be the second derivative of the angular displacement with respect to the time. So again, the convention that has to be followed is again the angular acceleration in the counterclockwise direction is to be taken as positive. But you must keep this thing in mind that it is not necessary that the direction of angular velocity and direction of angular acceleration will be the same. There may be a case where the direction of angular velocity and angular acceleration will be same, but it is not necessarily true. Let us say that initially, let's say that this is the vector. So initially the direction of the angular velocity is let us say that this is the omega direction. So after some time this angular velocity change to new vector, which is omega prime, let us say that. So what will be the angular acceleration? Is this angular acceleration will be simply the difference between omega and omega prime. This will be your alpha. So in this case alpha is not in the direction of angular velocity. So there may be a case that angular acceleration and angular velocity have the same direction, but it is not necessarily true. So as in the case of the rectilinear motion, when we talk about when the acceleration will be function of velocity, so when acceleration will be the function of velocity, we discuss the relationship a ds equal to v dv. So similarly, in case of the rotation, when the angular acceleration become the function of angular velocity, then the relation will be alpha d theta equal to omega d omega. So how can we get this relation? As omega is equal to d theta by dt and alpha equal to d omega by dt. So in the first equation, write the equation in term of dt. So this equation become dt equal to d theta by omega. Again write this equation in term of dt. So dt equal to d omega by alpha. So equate the two equation, d theta by omega equal to d omega over alpha. So this become alpha d theta equal to omega d omega. So in this way this relationship is derived. So this relationship will be used when your angular acceleration will be the function of angular velocity. So this is about the angular acceleration. So when also from the for the rectilinear motion we discussed the equation of the motions. So similarly, when the for the rotation motion we also discuss the equation of the motions. So equation of the motion, when the angular acceleration alpha is constant, then this equation will be omega equal to omega naught plus alpha time t. Here where you have to simply replace v with omega and a with alpha, and in this and simply s with theta. So in this way you can get the equations for the angular for the equation of motion when the angular acceleration alpha will be the constant. So this is for the uniformly accelerated motion. For the uniformly rotation motion, when your angular acceleration will be 0. So when your angular acceleration will be 0, the only equation will be like when your angular acceleration will be 0, this term will be the 0. When your angular acceleration will be 0, this will be 0. When your angular acceleration 0, this term will be 0. So the only equation that you get is theta equal to theta naught plus omega naught t, which shows the relation between the initial displacement and the final displacement. In this case here, when the angular acceleration will be 0, your initial and the final velocity will be the same. Again from this equation your initial and final velocity will be the same, but your initial displacement and the final displacement will be related using the relation theta equal to theta naught plus omega naught time t. This is for the uniform rotation, and these three relationships are for the uniformly accelerated rotation. So this is all about the equation of motion for the rotation of the rigid body about fixed axis. So in the next slide we will discuss rotation about the fixed axis, rotation of rigid body about the fixed axis in detail, in which we will derive the velocity and acceleration. Now come to the main topic, which is rotation about fixed axis. Now consider that you have a rigid body. Let us suppose that this is the rigid body and this is the axis about which this rigid body is rotating with an angular velocity omega. Now consider that you have a particle P on this rigid body. Let us say that this is the particle P on the rigid body. So what will happen when the rigid body rotate about the axis? Let us say that the axis name is AA prime. So what will happen to the particle when the rigid body rotate about an axis with an angular velocity omega? As we discussed in the previous lecture that this rigid body when rotate about an axis with an angular velocity omega, the particle has to follow a curvilinear motion. This means that about this axis this particle has to travel in a circular motion. Let us say that it has move in a circular fashion about this axis, and let us say that the axis the origin of the center circle is, this is O, which is the origin of the circle. Now what will be the position of the particle P from the point O? So it will be R, which is the radius of the circle. Now after some time, let us say that this particle P move from this location to a new location. Let us say that the new location of the particle P is, this is P prime, which is the new location of the particle P. Now again the location of the particle from the origin is denoted by R. So initially let us say that the point on this, let us say that this is the fixed axis about which the angular displacement of the particle P is measured, and which is simply theta. Now when this particle P move from the current location to a new location P prime, then there occurs a change in position. So the change in position we can write is d theta. And what is the change in displacement? This will be change in displacement, which is equal to ds. So we can write as ds equal to r time d theta. We can write as ds equal to r time d theta. So by dividing both sides by dt, what we get, what is ds by dt? It is change in position with respect to time. So this will be equal to magnitude of velocity. R is simple constant. What is d theta by dt? Rate of change of angular position. This will be equal to angular velocity, which is r omega, which is omega. So this relation become v equal to r time omega. This is in scalar form. This is the magnitude of velocity. So what will be the vector representation of the velocity? And this magnitude of velocity will be tangent to the this circle, and this will be, let's suppose this is the velocity v which is acting, and this will be tangent to the circle. So in vector form, how can we represent this velocity? So let us say that you have another point on this axis. Let us say that that point is, let us say this is the new point. Let name that is q. And from this point, which is on axis of a prime, what will be the position of the particle p? You have to draw the position vector. So the new position vector, let us say that this is the position vector, which is represented by rp, which show the position of the particle p from the axis a prime. So this position vector rp make an angle phi from the axis of rotation a prime. So this triangle become, this is rp, it make an angle of phi from the axis of rotation, and this is your radius r, which is the radius of the circle. So what is the magnitude of r in term of rp? R will be equal to rp sine of phi. This will be the magnitude of r. So in the previous slide, what we got, v equal to r omega, and the relation of r with rp is r equal to rp sine of phi. So we can simply substitute the value of r in the velocity equation. So the velocity equation become v equal to omega time rp sine of phi. So what does this mean? So let us consider that you have two vector a and vector b. So when we take the cross product of the two vectors, then the cross product of the two vector a and b simply become ab sine of theta, where b sine of theta is the projection of the vector b on vector a. So similar to the relation of the two vector, the cross product of the two vector a and b, we have the relation of omega and rp, which is omega rp sine of theta. So this means that the velocity is the cross product of the two vector in the vector forms. So this means that v equal to omega cross rp or rp cross omega. We have two conditions possible. What are these conditions? Omega cross rp or rp cross omega, as we have no clue about whether it is the cross product of omega and rp or rp and omega. We just got the clue that it is the cross product of the two vectors by using the relation of omega rp sine of theta, and by approaching this relation to by comparing this relation to the vector cross products. So what will be the velocity vector representations? So how can we got an idea about whether it is omega cross rp or rp cross omega? So we can get the clue about this by using the right hand rule. So as omega is about, this body is rotating about an axis, let us say that this axis is a prime. So this rigid body is rotating about this axis in anti-clockwise direction with the angular velocity omega. So when you curl your finger in the direction of omega, your thumb point the vector of the omega. So this means that the omega vector is acting in the along the a dash. This is the omega vector. So omega vectors is simply equal to omega time k. Let us say that this x vector, we call this axis is z axis, so it will become omega time k unit vector. So how can, and this velocity, and the velocity v is tangent to the circle. So how can we cross product r and omega? So cross product rule, right hand rule is that point your hand in the direction of the vector. So first case is omega cross rp. So you have to point your hand in the direction of omega. So when you point your hand in the direction of omega, now turn your palm in the direction of rp. So when you in such a way that your palm is pointing toward rp direction, and rotate your fingers in the direction of rp, starting from omega in the direction of rp, so that your thumb point the cross product direction, which in this case is velocity direction. So in this way you can get an idea about the cross product of the two vectors. So when we cross multiply omega and rp, we get the direction of the velocity similar to the this velocity direction. And when we cross multiply rp cross omega, we get the direction of velocity out from the slides. So since this particle is moving in anti-clockwise direction, this means that the direction that we got this out from the board is not possible. So the only direction which is possible is tangent to the circle, and it will be in the counterclockwise direction. So this means that the velocity vector is v equal to omega cross rp. This is the simply the vector that we got for the velocity. So this is the velocity representation in vector form. So here is the radius r, the position vector r. This is the position vector r. It lies in the plane of motion. So we can simply write the above equation is omega cross r, as r is in the plane of the motion. And this is the special case in which the position vector r can be chosen for rp. This is the special case. And since r is lies in the plane of the motion, so we can simply write as v equal to omega cross r. So this is the velocity of the for the rotation of the rigid body about fixed axis. Now in the previous slide we discussed about the velocity for the rotation of the rigid body about fixed axis. Now what will be the acceleration in case of the rotation of rigid body about fixed axis? So as we know that acceleration is simply the time derivative of velocity. So the velocity equation that we got is omega cross r. So this means that it will be the time derivative of omega cross r. So here we have two vectors and that are changing with respect to the time. So we have to take the cross product. We have to take the product rule to take the derivative. This means that a will be equal to d by dt of omega cross r plus omega cross d by dt of r vector. So what does this means? Omega d by dt of omega, rate of change of angular velocity with respect to the time. So this will be the angular acceleration. So this term is showing us alpha, where alpha is the angular acceleration. And what is dr by dt? This is the rate of change of the position vector. So it is simply showing us the velocity vector v. So we can write acceleration as a equal to alpha cross r plus omega cross v. So again in this equation we can substitute the value of v. So when we substitute the value of v, a become a equal to alpha cross r plus omega cross, what is v? V is omega cross r. So we can get the triple product of the vectors omega cross r. So this is the acceleration equation. So what is this alpha cross r? So when we take this alpha cross r as the by using the right hand rule, and you have to point your vector, your hand in the direction of the vector alpha. So here this is the rotation of alpha. So the vector alpha will be this one. This is the vector alpha. So again alpha equal to alpha time k vector if we take this axis as z axis. So again, when you take the right hand rule in the, and your hand is pointing toward the alpha direction, and point your thumb in the direction of R. So, and curve your finger towards R direction. So it means that it's showing us the tangential acceleration. So this means that this is the term which is tangential. What is omega cross R? This is simply the omega cross R is V, velocity, which is tangent to the circle or tangent to the path. So let us say that this is the circle and this velocity is another, any point it is tangent. So what is V? So what is omega? V is the tangent to the circle. And what is omega? Omega is simply, let us say that this is the omega which is pointing out from the board, as this body is rotating about an axis which is pointing out from the board. So the direction of omega will be pointing out from the board. So when you take the cross product of omega times this V, this means that your thumb is pointing towards inner direction. So what will be this inner direction? It is normal to the circle or normal to the path. So this means that this velocity term is showing you the, this acceleration term is showing you the normal component. So this is in the vector form, while in the scalar form this A is equal to, what is alpha cross R? This is R alpha, yeah, alpha R, you can simply write, plus what is omega cross R? Omega cross R is V, but in term of omega we can simply write this equation is minus omega square R. And why this minus sign? Because it is acting in the negative R direction, like in the decreasing R direction. So that's why here we have to put the negative sign. So if you are talking about the normal and tangential coordinates, no need to write this negative, you have simply write the positive sign. But when you are talking about radial direction and the theta direction, you have to put the negative sign, as this acceleration an component is acting in the negative R direction. So this is all about the acceleration of the rotation of rigid body about fixed axis. Now, what is the procedure for analysis for the case when the rigid body rotate about an axis? So the first step is that you have to establish a positive sense of direction. The positive sense of direction is the convention we followed it for the omega and alpha. The anti-clockwise direction is to be taken as positive, but it's up to you. You can change this direction, but you have to clearly mention in any numerical that the direction you have chosen is either a counterclockwise direction as positive or anti-clockwise direction as positive. So after establishing the positive sense of direction, so use the relationship which for the angular velocity, acceleration, angular position, and when the angular acceleration become the function of angular velocity. The equations or the relation will be omega equal to d theta by dt, alpha equal to d omega by dt, and alpha d theta equal to omega d omega. This relationship will be used when the alpha is the function of angular velocity. This relationship will be used, and when this velocity will be the function of angular position, the first relation will be used, and when the angular acceleration will be the function, sorry, this will be the function of theta. When acceleration will be the function of theta, this relationship will be used. So when the angular acceleration will be used as a function of omega, so the second relationship will be used. So when the angular acceleration will be function of the angular position, the third relationship will be used. So after that, you have to notice about whether the rotation is uniform rotation or whether the rotation is uniformly accelerated rotation. When the rotation is a uniform rotation, the only relation you have is theta equal to theta naught plus omega time t, and omega naught equal to omega. But when the angular acceleration is constant, which is the case of uniformly accelerated motion, you have three relationship, and you can use any of these relationship to find out the unknown. So after that, when you find out about omega, what will be the alpha, and what will be theta, so you can simply find out the velocity of any particle p on the rigid body by using the relation v equal to r omega, and tangential acceleration is alpha r, and normal acceleration is omega square t. So these are the relationship that you can use to find out the velocity and acceleration of the particle p on the rigid body. So in such a case, that when the rigid body rotate about an axis, and if the geometry of the problem is difficult to visualize, so you can use the relationship in the vector form. So in the vector form, you must keep this thing in mind that you have to use right hand rule. And in the right hand rule, you can simply, for first thing is that, like if you have two vector, a vector and b vector, and you want to find the cross product of a with b, so you have to point your hand in the direction of vector a. Now rotate your hand in such a way that your palm is directing toward the vector b. Now rotate your finger in the direction of b. Now in this case, thumb will point you the direction of the normal of this a cross b. Have you got this thing? So this is the all about the rotation of the rigid body about fixed axis. So in the next class, we will discuss some numerical and the general planar motion of the rigid body.